Part A, it is going at a constant velocity. That means the forces are balanced due to Newton's first law. So in the free body diagram, there's the bucket, there's gravity down. That has to be balanced out by the tension. So basically, whatever the gravity is, that has to be the same number as what the tension is. And that would equal to m times g. That would be 49 newtons. All right, and that would be pointing upwards. B. So what if this bucket is speeding up at 1 meter per second squared down? So there's an acceleration here. The acceleration has to be down for it to be speeding up because it's being lowered. So this time, the free body diagram, since the acceleration is down, the downward force has to be larger than the upward force. So I'm going to draw the tension shorter. I'm drawing the gravity arrow the same size approximately as in the part A because the gravity is not going to change. So it's the tension that's getting lower, which is going to allow this to speed up falling down. Okay, so how about I do this one in terms of vectors, and part C I'll do it in terms of magnitudes only, so you can see the difference here. Okay, so part B, I'm going to apply Newton's second law. So F net is the net force, is defined as the sum of all of the forces. So we use a plus sign to represent sum. That is the correct statement when we're leaving everything as a vector. Now, the net force is going to equal to m times a. And actually, I will change the force of gravity as well as to mg. Now, which way is mg? Mg is down. So I got to add that in here because I am working with vectors. So if I just write mg, that doesn't have a direction to it. So I'm going to add the direction down. Okay, I'm going to fill in some numbers here. So the mass is 5.0. The acceleration is 1 meter per second squared down. 1.0. I'm just going to fill in the direction of down. Equals mg, 5.0 times 9.8. Also down, because that's gravity, plus the tension, which, well, that's what I'm solving for, I believe, so I'll leave it as tension. Okay, so then I'll just do the computations. So on the left side, 5 times 1 is 5. This would be 5 newtons down. And on the right side, 5 times 9.8 is 49 newtons down. And I will isolate for tension, which means I will subtract the 49 newtons from both sides. So 5 minus 49 is negative 44 newtons down, or 44 newtons up. So that's how I would do it if I left everything as a vector. Whereas if I work with what I personally find more intuitive, which is using magnitudes, maybe we can see the difference here. So in part C, the bucket's still moving down, but now it's slowing down. So the acceleration is 1.0 meters per second squared up. So there's still gravity going down. It's still m times g. But now it's slowing down, so the tension is going to be larger. It's got to beat the gravity so that it can slow it down as it's falling. So this time, instead of working with full vectors, I'm working with magnitudes of vectors. So I'm going to write the magnitude of the net force. So this means how long is the net force arrow? How long is the net force arrow is the symbol that I just wrote down, F net surrounded by magnitude bars. And how long the arrow is going to be is, intuitively to me, it's going to be the length of the longer arrow subtracted by the length of the shorter arrow. And because they're in opposite directions, I subtract. So the downward gravity is going to cancel out part of the upward tension. So if I'm just looking at the lengths of the arrows, the resultant length with the length of the long one minus the length of the short one. So that's how I would write it in terms of magnitudes. And the big difference between this and part B is that part B, there's a plus sign in between them. In part C, there's a minus sign, and that has nothing to do with which way it's accelerating. It has everything to do with my choice of whether I'm working with full vectors or if I'm working with just the magnitudes. So I'm going to continue this here. I will replace net force with MA, the magnitude version. Tension is what I'm solving for, so I'll leave that. And I will replace FG with MG, just the magnitude version. I'm not needing to add a direction here. Now I'll isolate for tension. That'll be adding mg to both sides. And that will be 5 times 1 plus 5 times 9.8. It's 5 times 1. It's not 5 times negative 1 because it's the magnitude of the acceleration I'm looking at. Magnitude does not care about positives and negatives. So that'll be basically 5 plus 49, which will be 54 newtons. And I know this is just the magnitude. You may say, oh, don't we have to give the answer, the direction in the answer? Well, the direction is going to be up. So the disadvantage of using magnitudes is you kind of lose the direction in your steps, but you can just add it back at the end because it's kind of intuitive. I know this thing's accelerating up, so I know that my tension is going to be up. So I can just add that in at the end like this. That would be the final answer.